All right, silly people, here's the situation. This is the formal definition of a Hermitian conjugate of the operator Q, right? And we're going to be using it to find a bunch of Hermitian conjugates of various things. And that's pretty much it, yeah. Finding a bunch of Hermitian conjugates. So, first bit is we need to find the Hermitian conjugate of X, just X, like a position operator. So I mean, this is saying that what if X was an operator, which it is, what is the situation in where the inner product of F with xg is equal to x dagger F uh, g, inner product of that. And for a lot of these, just look at the integral definition of the inner product instead of the inner product notation, because if you turn it this way, then you know that it's the uh, integral dx of f star with x acting on g, um, right? So if we just moved that x to the other side of f, that's how you know it would be x f star g. In other words, it would be just the same thing as the operator x acting on f inner product that with g. In other words, X is its own Hermitian conjugate. It's the same thing, which is, I kind of did that in the last video, but nice to see it explicitly. Um, Also, we need to find the Hermitian conjugate of I. If we treated I as an operator, what would the Hermitian conjugate of that be? So let's just again write it out. So inner product of f with ig. If we put it in the integral notation, it would be inner product, or it would be integral dx f star I g, right? Uh, and you know that if we really wanted to have the complex conjugate of I, it would be minus I, right? You would just switch the sign on the I. So you could group the inner product of I with f here. I mean, group it together with f so that you can have a complex conjugate there um, with g. And then you know that you can just write that as uh, minus I acting on f with g, which just goes to show you that the Hermitian conjugate of I is minus I, which you kind of should have figured that out given that the Hermitian conjugate is just complex conjugation plus transposing. So if I was just a matrix, you would just switch the sign on the matrix and you get the same thing, right? Um, then finally, we need to find the Hermitian conjugate of d dx. This is an interesting one, actually. So again, we'll set it up. The inner product of f with d dx g. If we write it in integral notation, is the integral dx f star d g dx, right? And if we do integration by parts on this guy using u equals f star, du equals then df star dx, dx, and dv would have to be, in that case, dx dg dx, and then the integral of that, so v would just be g. So you would rewrite this integral as being uf, so, or uv, uh, f star g uh, integrated at the endpoints, which should go to 0 if they're both well-defined wave functions, minus the integral dx of v du, which in this case is g df star dx. Okay, so if we just group the minus sign into the integral now, we can see that this is just minus d dx acting on f star multiplied by g. So that should tell you now that the if you put it back into inner product notation, that it's minus d dx acting on f inner product that with g, and that tells you that the Hermitian conjugate of d dx is minus d dx. We're going to prove some Hermitian conjugate stuff that I kind of used in the last video without really showing how they work. And that is, first of all, we're showing that if you take the complex conjugate of two matrices multiplied together, then you get back out the Hermitian conjugates of the second matrix times the Hermitian conjugate of the first in that order, which is kind of wacky. And we'll show it by, again, just putting it in the inner product notation, inner product f with q, r, g. And so to accomplish this, what I'm going to do is make use of the fact that any operator acting on a vector is a new vector, right? So we can define rg, for instance, to be a new vector called h. And so this f inner product with qrg is equal to f with qh, right? Which we know by the definition of the Hermitian conjugate is equal to q dagger f h. And then we can expand h back out to this, to rg, right? And then we're going to do a similar thing where now we're going to define q dagger f, as a new vector called j, which we put on the left hand side of the inner product. So now this equals j rg, and then again, you know by the definition of the Hermitian conjugate that this is going to be equal to r dagger j with g, and then you can expand the definition of j back out and you see that it's r dagger q dagger f with g. So yeah, that just proves this, that if the whole, like if we took this inner product and Hermitian conjugated the whole thing, we would get this. So it shows that this is true. Pretty cool. We also need to show that if you take the Hermitian conjugate of a sum of two operators, that the conjugation just distributes and you get q dagger plus r dagger. This is, again, I'm going to accomplish it using the definition. So inner product f with q plus r acting on g, which by definition is equal to q plus r dagger on both of them, inner product acting on f with g. But it's also equal to, if you just distribute the vector to be multiplied by both of the operators, this is the inner product of f with qg plus rg, right? Which means it's equal to, if we split the inner product up now, it's going to be f with qg plus f with rg. And then using the definition of the Hermitian conjugate, this is now equal to q dagger f with g plus r dagger f with g. And then we can use the same principle as splitting it up to put it both into the same inner product. And now this, you see that this is q dagger f plus r dagger f with g. In other words, in parentheses, q dagger plus r dagger acting on f inner product with g, which means that we've gotten down to this form here. So it's showing you that indeed q plus r, if you take the Hermitian conjugate of it, you just get q dagger plus r dagger. Right. So that's should be it for that bit. Oh no 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 no! We also need to show that if you take the Hermitian conjugate of CQ, where C is a complex number, then you get C star uh, Q dagger. This may seem obvious, but I'll do it anyway. So writing it out, it's F C Q acting on G. And you can just move the C out of the inner product because it is just a complex number. So you can instead call it Q inner product with QG, or F inner product with QG with a C on the outside, which you know is going to be equal to C Q dagger acting on F with G. Um, and if you wanted to have C inside the bra rather than inside the ket or outside of the inner product, you would have to take the complex conjugate because uh, the bra, any C number that's in a bra has to be the complex conjugate of it if it was in a ket. So it's C star Q dagger F with G. And so, yep, that's the Hermitian conjugate of QC. Turns out uh, not too bad. Um, Now we get to do the fun part of the problem, which is constructing the Hermitian conjugate of the raising operator from chapter 2. This is one of those harmonic oscillator things. And it has the form like this. It says a plus is equal to 1 over the square root of 2h bar m omega times minus I p. The p is the momentum operator plus m omega x. And we need to find the Hermitian conjugate of that. So the Hermitian conjugate of the raising operator then, it's going to not hit any of these constants because the Hermitian conjugate of a real number is just the same real number. But we do have to take into account that it's the Hermitian conjugate of what's in the parentheses, right? Um, so, and then I'm just going to hone in on this because this is the important part. So this, we know that if you have the Hermitian conjugate of two summed operators, then it's just the sum of the conjugated operators, right? So we know that it's the Hermitian conjugate of minus IP plus the Hermitian conjugate of x. And then x is multiplied by a couple of real numbers, which the Hermitian conjugate doesn't really hit. So the minus IP, if we're treating both the, and also there's no reason to keep the minus sign inside the Hermitian conjugation either. We can pull it out and it'd be equivalent. And if we treat I and P both as operators, and we kind of should because we're doing a Hermitian conjugation, we need to switch the order of their multiplication. So this is going to become minus P dagger, I dagger, plus M omega, and then the Hermitian conjugate of x was just x, right? So we need the definition of the momentum operator now, as it turns out. That's just minus I h bar d dx, and that's being conjugated. The Hermitian conjugate of I is minus I, and we still have it plus m omega x. I'm going to hone in on this chunk now because the m omega x isn't really going to change much this whole time. So this chunk, I count 3 minus signs so that we get a minus sign. We also get an h bar because the Hermitian conjugation isn't going to hit that. We also get an I from over to the right. So minus h bar I. And then we have to do the conjugation of the stuff inside. So that's going to be d dx dagger times I dagger. Um, okay, and then the Hermitian conjugate of d dx we found was minus d dx, and then the Hermitian conjugate of I we found was minus I. I'm still counting 3 minus signs, so we're still going to have a minus, and I'm going to group all the i's together like this. So it's going to be minus I, I, h bar, d dx. And even I'm going to have the minus sign attached to this I for reasons that will become clearer, because this is just the definition of the momentum operator again. So we can write this as equal to IP, which means the stuff without the constants is just IP plus m omega x, which means the raising operator conjugated, is 1 over square root 2h bar m omega just IP plus m omega x. Right. And so this is also the definition of the lowering operator. So that kind of makes sense that the conjugate of the raising operator is the lowering operator. So I think everything turned out pretty nice. All right.